Good afternoon, everyone. Welcome. It is my pleasure to host and introduce our speaker today, Eric Bittner from the University of Houston. So Eric is a distinguished professor of chemical physics and currently holds the Hugh Roy and Lillian Kranz Cullen Professor of Physics Chair. Throughout his career, he spent time at UT Austin, University of Cambridge, École Normale Supérieure, and Los Alamos National Lab. He's a fellow of Royal Society of Chemistry, the AAAS, and APS. At Los Alamos, he was the Ullum Distinguished Scholar and the Center of Nonlinear Studies. So Eric has a long history of studying open quantum systems, theory of such, and particularly molecular systems, in some cases relevant for organic electronics that we have on our phones and on our bodies. Recently, he's turned his interest to strongly coupled systems, including polaritonic systems. And today he's going to tell us about noise in quantum systems, including excitons and polaritons, and explain to us how noise can be a feature and not necessarily just a bug. Now, Eric is a very dynamic person. He's got a lot of interest. He likes to rock climb and mountaineer. He's been up Long's Peak. He's been up many of the Flatirons. He's taken up astronomy. And recently, he's taking up sword fighting. And he's very skilled at sword fighting. So I suggest you keep the questions polite when we're done with the talk. So please join me in welcoming Eric.
Yeah, it is true. I did take up sword fighting a number of years ago, mostly historical sword fighting. So be careful. I can, whatever. So today's really talk in two parts. The first part, which I'll call the aperitif, is some investigations we've been doing in developing the theory for what I hope would be a novel form of spectroscopy, where we try to harness the quantum mechanical entanglement of photons as spectral probes of some sort of material process. And one of the questions, this really came about very much experimentally motivated, to some extent theoretically motivated by work by Shalom Mukamel and et cetera, maybe starting about a decade ago, where we were sort of playing around with this idea. What kind of information can be learned? Can people do spectroscopy in the normal sense that we would like to do spectroscopy with ordinary laser type systems? And one of the questions that came about was before you go off and invest millions and millions and millions of dollars on a quantum light system where your signal to noise ratio is really pretty much in the basement, is there anything that we can learn? And what kind of things can we learn, or can you learn, that's difficult or non-trivial to get using ordinary, much cheaper $1 million type probes of light? Okay, not that it's an easy experiment. So how would you actually do this? I'm just going to jump in. There are different kinds of experiments that people have been doing. Obviously, quantum light, maybe not so obvious, is a driving force for how we think about quantum entanglement, and maybe even harnessing the properties of quantum light for doing quantum computing, quantum cryptology, quantum communications, and et cetera. I'm not going to talk about that. I want to focus on the idea of using this as a spectral probe for doing chemical physics type problems. And so one way you can imagine this is that you have an input quantum state of light. Now, I don't know what it is. It's just an input quantum state. And you pass it through, for example, maybe an optical cavity that has the system in it that you want to study. And you look at the statistics or the properties of the output photon state. Now, this is, my background is in scattering theory. And so this looks to me like a scattering theory problem. And that's exactly how I think about this. You can have spectrally entangled photons that are, for example, in this little sketch we have here. Okay, my classical laser pointer has been replaced with a quantum laser pointer, I guess. Let's see, it makes it go here. Okay. I don't like to use green light because of the fact that some people are, you can't see green. Okay, so I apologize if that's the case. But maybe there's some sort of state inside of the cavity. We'll call them polaritons. We'll call them polaritons. They interact somehow because you're creating excitations in a common media. Maybe there's some sort of many-body interactions, which is simply going to call many-body interactions, left generically defined And I leave and I detect these using some sort of coincidence measurements. And hopefully that coincidence measurement is spectrally resolved, where I can look at the correlation between an output photon at one frequency, or polarization if you choose to use polarization entangled photons, and its complementary photon in the other channel, and these have been called signal and idler modes for historical reasons. And I imaged them on my little laptop over here. And we'll call that the joint spectral amplitude in the output state. So the idea of a theory would be you create some sort of entanglement using spontaneous parametric downconversion, creating pairs of photons. And this is a well-known and well-studied type system. You pump like a crystal that is as a chi2 type characteristic, creating entangled photons, look in the right place on this cone of photons that's emitted. That creates a joint spectral amplitude for an input state that is propagated in using this little thing called a Muller operator, which is really something that allows me to connect asymptotically the state at minus infinity. Here I've written in terms of some sort of input Green's function to my sample, which whatever it's going to be. And these two things must be equal to each other at time t, z, if I do this in some sort of Fourier representation. And this is like the beginning of a very long scattering theory type problem, if you want to look at it that way. Now, to put this in a little bit more concrete sense, this is some experimental data. It's always a bit daunting as a theorist to start off a talk with experimental data, but I'll do that. This is data that my good friend and colleague Ajay Kandata, who is at Wake Forest, has been working on, where they pass entangled photons through a microcavity device that they have, and you see a filtering of and change of the input signal to an output signal. There's some wiggles and all other kind of stuff. This is not an easy experiment to do by any stretch of the imagination. And our question was, well, how can I correlate whatever this thing is to some sort of thing over here? Here's my input pair of photons, and this is what's actually measured, but there could be some sort of non-separability induced due to some sort of interaction, which I'll call gamma to the gamma 4, which I'll explain why that has to be that notation in a moment. But it's something that simply transforms an input state to an output state, resulting in some sort of entanglement. Now, we played around with this idea, oh boy, at 3 BC, 3 years before COVID. 2000, there we go, 2019, 1 BC. So this is almost 1 BC, 1 year before COVID, we started playing around with this. I don't think these actually work, by the way. I think I had to pay money to get those to continue to work. So if you're going to try to look up the paper by scanning that, it's not going to work. But here's the idea. So let's imagine that you have a pair of photons that are coming through a sample. The easiest thing that's going to happen is they don't care about each other. They go, one photon goes through the sample, another photon goes through the sample. Typical linear response type things happen to it, Rayleigh scattering, absorption, anything that's going to happen. Any sort of typical one photon type transition goes through the sample, comes out at a different frequency, comes out at different, they don't care about each other. I get separable output states. There's no entanglement. Maybe there's some sort of interaction that I don't know about. So I'm just going to denote that by a spring because LaTeX allows me to draw springs, okay? And I'm going to put a bunch of springs in between. Each one of these springs allows you to say, I've got some sort of impulsive interaction due to this excitation in the system knowing about somehow some other excitation in the system interacting through the media through some sort of unspecified at the moment channel. And if I do this, I can resum this very easily, and I get this nice expression, psi being the magnitude of the interaction in some sort of phase that I pick up due to the complex nature of the interaction. And I can resum all that, and I can calculate the von Neumann entropy related to how separable the output entanglement happens to be. And what was interesting in this is that your von Neumann entropy, which is in principle something that you would infer or be able to calculate from the joint spectral amplitude, is directly related to this interaction parameter. So now I have a one-to-one mapping between a spectroscopically observable term, a number, and a number that I can talk about in terms of intermolecular or some sort of intersystem interaction between these different kind of photons, maybe polarizations or other sort of dynamics going on in the system. Now at the time, I didn't know what that interaction was. And so that's never stopped me. So we decided to play around with this a little bit more. So this is more recently, 2025, we published this in PRA, where we take again the same sort of idea. And this is like a Tavis-Cummings model, if you're familiar in optical physics, where you basically have an ensemble of two-level absorbers in the system. You have a common cavity mode, and everybody is talking to, and you excite the system. You pump photons into the common cavity mode. They interact with the spins or the excitations in the lattice, and then I emit back into the output photon states. And I can work out the equations of motion for that, Heisenberg equations of motion, et cetera, and eventually calculate the correlation matrix that you would have in a Bittner function describing the output state. Theoretically, we do this using the Lyapunov equations. And again, I invite you to read through this very nice but pretty technical paper that Samir wrote just recently, where we show how you can use this Muller operator idea to propagate an input correlator to an output correlator, okay? I'm not going to walk you through the machinery of that, but we can do that. That allows us to take, what was really nice about this particular piece of work is that it allows us to take experimental data and plug it through the machinery of our Hamiltonian, if you want, play around with the parameters of our Hamiltonian, which I admit I really don't like to do. But when you have students that like to do machine learning and this kind of stuff, they like to do this kind of stuff. We could play around with the parameters of our model and eventually get something that starts to look like the experiments by adjusting a few of the internal workings, the inner workings of our model. And this really sort of got us thinking that, well, if we can do that for something that's nice and simple and relatively, parametrically defined, can we play around with a little bit more details of the system and come up with a much more interacting, realistic many-body model that maybe allows me to take, with the same sort of idea, the same sort of philosophy of taking an input state and calculating what would be the output state, and then using either single value decomposition or machine learning or something like that to say something about the inner workings of the actual system, which is a common spectroscopic problem. So here's the model that we want to propose. So imagine that you have a medium. Okay, in this case, it's going to be a topological insulator that I'm going to model as a Suschiefer-Heeger chain. If you've not studied the Suschiefer-Heeger chain, it's a model for polyacetylene that was developed in the late 70s that explains the dimerization of acetylene. So you have short, long, short, long, short, long type bonds in polyacetylene. This has some really interesting topological properties. This is a really nice model in condensed matter physics or solid state physics, the two-band exciton model. And you can calculate band structure. It's really straightforward to do. But what's fun about this model is that there are two regimes for this model demarked by a metallic state where the band gap closes exactly. So you have a normal state where one hopping integral is large compared to the other. So let's say T1 is large compared to T2. So the intra-cell versus the inter-cell. So the intra-cell would be between cells, the inter-cell would be within the cell. Hopping integral is strong. I can switch that and make so that the hopping integral out of the cell is larger than the hopping integral inside the cell. I wind up with a state that I can describe with this kind of band structure, or if I put this onto a different kind of representation, represent this matrix on the complex plane. This now circles the origin, which means I have a winding number, a topology that is imposed upon the physical system by the nature of the coupling. And one of the questions that we were playing around with Andrei Piertinsky at Los Alamos was whether or not maybe these entangled photons can be a probe of this kind of topology. Can we see using this kind of spectroscopy evidence of topologically protected states? I don't know. Let's see. So here's the model. So we have input photons, just like I was describing. They come into the cavity. Each photon, I create pairs of excitations within the Sushi-Verheger chain. There's an interaction, which I'll describe in a moment, and then I get output photons that I will eventually try to measure, or somebody will try to measure. Now, how do these things interact? Well, an input photon can create virtual electron hole pairs within the medium, with the polariton-forming medium in this system. And when you have an electron hole pair, I mean, this is like a little polarization in the system. So if I have another polarization within the system, there's an attractive or maybe repulsive interaction between these pairs of polarizations, and that leads to the entanglement between these two output states. Let's test that. Let's come up with a theoretical model for that. Why do I think that this topology thing might matter? So my longtime collaborator Carlos Silva and I have a paper that's pending still, JPC letters. This is like one of the problems of Carlos, writing papers with Carlos. Carlos sometimes gets really busy and we forget to update the revisions, and then it has to be resubmitted and everything else. So anyway, one of the things that we looked at was, well, what if we look at Sushi-Verheger not in a cavity, just try to look at what would be the nonlinear spectroscopy that one would have in the Sushi-Verheger model. By the way, this is this Hamiltonian for the Sushi-Verheger model. And what we found is if you look at like the third order response, but not the third order current response for the system, so this would be analogous to the third order response that you would have in an optical response of the system, but you have to do this with regards to the current operator because it's a continuous system. And you look at the response at zero frequency or around zero frequency. What's interesting is that there's a phase shift between the topological phase and the trivial phase in the response of the system, that you don't see in the optical region of the spectrum, but you definitely would see in around the DC response region of the system. So this got us sort of thinking, well, maybe there is something that one can probe using quantum light that here we go. We can see a definite signature of trivial phase versus topological phase in the current response. Can one see evidence of this kind of phase in the response that you might get with quantum light? So here's our, I'll walk you through some of the calculations we do. So here is basically how I would describe the Sushi-Verheger model inside an optical cavity. So what the technique that we do is to use the Feshbach technique and marry this with the Keldysh Green's function technique. But at the end of the day, we wind up calculating a self-energy for the photons in the cavity. Mu is the current operator, not the dipole operator, it's the current operator. And this is then just a Green's function for the photon in the cavity. So delta is the energy gap of the Sushi-Verheger model as I move in K-space, in the crystal momentum space. And so this is then how a photon, a cavity photon, interacts with the system with regard, as if the medium is just simply a dressing the photon in the cavity, okay? And if you want to work this out in quantum field theory, this is what it looks like. You've got a photon that comes in, I create an electron hole pair, and a photon goes out, a little polarization bubble. And this idea that well, is this enough to see what you might ordinarily get with your typical polariton type models? Well, yeah, look at this. This is I was actually sort of pleased to see that you do in fact get your usual dispersion curves. You get an upper polariton curve, a lower polariton curve. The colored contours are the response functions that you calculate using this particular type of an approach. And sure enough, yes, you do see a marked difference between the predicted spectroscopy in a trivial phase versus the topological phase. And of course, like you want to jump to conclude that this is a topological effect. And I would argue that it's not a topological effect, And the reason is because any phasing effect is probably washed out due to this modulus here. What this is really reflecting is the change in the density of states that you have in the band when you're going from the trivial phase to the topological phase. So you get a lot more transition moment, if you want, in the topological regime that you would have in the trivial normal regime. You can see this if you just simply take a slice at k equals 0, and it says you see a shift. You don't really see, you just see a shift and maybe a change in the intensity. This is entirely due to the density of states, not a topological effect. So ordinary linear type absorption spectroscopy will not give you any sort of topological signatures, at least in this model. Where you can start seeing topological signatures is when you look at nonlinear models. Specifically, if I look at, for example, the photon nonlinearities, and I calculate what would be the response function or the self-energy of photons if I have multiple photons in the system. Well, it's actually not that hard to calculate because there's no other interactions in the system. This is a model I can work out by pencil and paper. You can say, well, here's the retarded Green's function or retarded self-energy for the n photons in the cavity. It looks a lot like what you would normally have, but you have to solve a set of self-consistent equations to get the frequency renormalization due to n photons in the cavity. This first term is actually the Kerr nonlinearity, which would enter into the Gross-Pitevsky equation if you had a condensate in a system. So in other words, this parameter is related to this guy, and which is now something I can calculate with my model, again, analytically. And what's interesting is, yes, there is a difference between, so the topological regime would be on this side, the normal regime would be on this side of 1. Differences in the strength of this nonlinearity, but what's also interesting in this particular case is that there's another transition that occurs in Sushi-Heger where I can go from a localized, so where I have very strong dimerization to localized states, delocalized electronic states, and again, on the other side, very localized states. You see very differences in the Kerr nonlinearities, and I don't know if there are experiments that show this. It would be interesting to know. I don't know that data point. Now, getting into the heart of the matter. Here's how I calculate here's how I calculate. This is it diagrammatically. How we can imagine thinking about how photons might interact within a cavity. So each photon going through the system creates a polarization, electron-hole pair, within this Sushi-Heger lattice. Okay, and then leaves at one frequency versus the other frequency. Now I can write out what this expression would be analytically, and here it is analytically. You can see here's the Green's function for one guy, Green's like self-energy for the other guy. And now what I don't know is this interaction term, but I can calculate that using density functional theory, time-dependent density functional theory, and the Berkeley GW package. We can calculate this. In fact, you can even fit the form of this to an analytical form if you take two excitons and allow them to be pulled apart just numerically. And you can find that this interaction takes a very nice Gaussian type form, which is consistent for basically like a screen Coulomb type interaction between these two polarizations. So the key parameters here are this range parameter, zeta, and the magnitude of this interaction, or the two parameters that would arise from electronic structure theory. So you can integrate this. It's sort of painful. You can use my favorite approximation, which is stationary phase approximation, which is sort of interesting that your two stationary points are related to each other. And if you sort of look at this, this is basically the threshold. The numerator, this is the threshold energy to create a pair of photons at that particular wave number. And then delta prime prime, or double prime, is basically the curvature of the band at that point. So these are, again, things that one can calculate directly from the band structure of and delta 0 is the band gap. And so you can calculate what this vertex is. And most of it is pretty benign. But the only part that really matters is really this Gaussian contribution part. And you can see where it's going to come about. And so you can, that's then the only part of the whole system that is non-separable. And so I can do single value decomposition on that, calculate Schmidt coefficients, run through the usual spectroscopy, and calculate an entanglement entropy entirely in terms of these normalized coefficients. And so now I have a mapping between what would be the entanglement entropy here, that again you could calculate from experimental data, do single value decomposition of your experimental data, calculate what the experimental entanglement entropy would be. From that, I have a handle for calculating that parameter right there, the range of interactions, the screening, if you want, or the range of interactions, rather, that determines how excitons within the lattice are interacting with each other. And I would claim that is something not trivial to try to get out of 2D spectroscopy. And just as a proof of principle, this works, at least theoretically. I don't have experimental data to play with this case, but I can take an input Gaussian to show that I can take a separable state and create a non-separable squeezing state through this particular process. And lo and behold, and this is just simply an analytical model that allows me to look at the logarithm of the entanglement entropy versus the log of this range, and this nice linear behavior, at least over multiple orders of magnitude. Now, I don't know offhand what the magnitude of this parameter would be, but you can go through and you can sort of make some arguments. You can say, well, this thing must be related to the exciton diffusion length. It has to be related to the line width of these things. It has to be related to the transition moment of the excitons themselves. So you can go through and make physical arguments to basically say that this number has to be someplace on the order between 0.1 and 10, something in there. And yeah, these are all of this is experimentally accessible if one can do photon experiments like this. Now, those experiments are not easy to do. My collaborator Ajay Kandata has basically bet his 10-year career on being able to do that experiment. I wish him luck. He has not done that yet, but he thinks that it's still within the realm of possibility. And I'm also not aware of other experiments that are able to do that data. So this remains a prediction. Okay. I'm not going to be able to go through all of this, so I will go through the main course, though. The main course is something that I started working on, again, 1 or 2 years before COVID. And it sort of like goes into my love, if you want, of metrology and even sailing and understanding how one keeps track of time and coming up with this idea of can you use environmental noise as a resource for enhancing and maybe preserving coherence in a quantum mechanical system. Some of this really worked out as an over coffee exercise when I was the Ulam Fellow at Los Alamos, sitting around on the blackboard, scratching out equations on the blackboard. And there's this really great quote by Stanislav Ulam that says something to the effect that it's amazing how you can sometimes change the world with a few equations scratched on a blackboard. I don't think this is necessarily world-changing, but it gives me a lot of inspiration for having casual conversations with people on different kind of things. Now, historically, and this is maybe very, very close to like bringing coal to Newcastle in a lot of sense, that I would argue this is one of the longest running scientific problems that was funded by a government, okay? And that is keeping track of time in an accurate way. We can go back to Stonehenge, if you want, keeping track of the seasons using monoliths of stone. But the sort of demarcation point comes with the work by John Harrison, who was a watchmaker, clockmaker living in England in the 18th century. This was motivated by a naval disaster in, and I'll get the year wrong, I want to say 1703, 1704, where roughly a third of the British Navy coming home from the Americas was lost in one day, not because of battle, but because of ships crashing into a Channel island because of a navigation error. Now, a midshipman pointed out this error. The captain of the fleet had him flogged. Okay, there you go. Such were the times. And this was because of a mistake made in navigation. Why? Why? So in order to keep track of time at sea, or why do we care about keeping track of time at sea? Who cares? You wake up in the morning, you pull on the sails. Well, you need to know where you are east or west. In order to determine where you are east or west of a meridian, passing through, let's say, some observatory or wherever you want, your home port, you need to know the difference between time at that meridian and time where you are locally. You need to know that accurately. An astronomical body moves across the surface of the Earth at 900 nautical miles in 1 hour. So you can track that down to figure out like how much error 1 second of your timing can be in terms of knowing your position on the surface of the Earth, right? You come out to like quarters of miles or something like that. So keeping track of time at sea was a big technological problem. This was partially resolved through this device, which was a double pendulum clock, motivated by earlier work by Huygens, Christian Huygens, and et cetera. And here's a fun little story. This is sitting in the Greenwich Observatory in London. It's a double pendulum. There's a bunch of springs and gizmos that whirl or whiz around. You can spend lots and lots of time. If you ever go to London, have nothing better to do, which I can't imagine not having something to do in London, but you just can't figure out what to do. Take the ferry, go down to Greenwich, go to the Greenwich Observatory, pay £20, and get a nice, beautiful tour, and you can see this device, okay? And this was the Generation 1 Harrison chronometer. It was the most accurate clock of its time. This is what it looks like. This was the final 1759 version. That is a very different clock. Now, if you're an experimentalist, another challenge I have to challenge for you is, God, this is beautiful, isn't it? Look at all this like filigree and all this. Do your laser tables look like this? I mean, engraved, look at beautiful, this, in his son's name on this. This is beautiful. Now, the problem is that there's actually a faceplate that goes over the top of this, so unless you are the person charged with winding this, you never get to see this beautiful artwork. Now, a bit of fun with this is that I spent so much time photographing this thing that a docent said, hey, what's going on? Why are you so interested in it? I said, well, you know, I do physics, I'm interested in all this kind of stuff. And then he said, well, would you like to come back and help us wind this clock? I'm like, yeah, of course we are. So I could put the white gloves on and oh my God, this is a 300-year-old piece of equipment. Just a couple other pictures of the Greenwich Observatory. This is the prime meridian. In fact, this telescope was built by Airy, function Airy, Sir George Airy. And you can stand right there, somebody who's in the east or west hemisphere right here. And just for fun, if you, we all have iPhone. Who all has an iPhone? Who all navigated sometime today using GPS? Everybody, right? How do we get to find a coffee shop using GPS, right? We all did. Okay, getting to this building, oh, where is it? GPS. So if you pull your phone out and you stand right here on the prime meridian, which separates the east and west hemisphere, this is the eastern hemisphere, western hemisphere, pointing north here. What do you think it's going to say in terms of east or west? You expect it to say 0.00000 east, right? No, it does not. That line is right there. Why? Why is that? Well, it turns out that here's where the actual planet, the actual prime meridian is. So I walked over to here until my iPhone said 000. It's really close to the statue of Yuri Gagarin. and a little coffee place here. But this is where, and the reason for that is that your actual GPS meridian is based upon a mathematical model of the Earth and not the location of this meridian. Now, it also turns out, just again for fun, because this is a colloquium, we can talk about colloquial stuff. There are multiple meridians. In fact, every single one of us has a meridian passing through us. There are multiple meridians that are by standard that go through the Royal Observatory. It turns out that our 0, line that everybody looks at for navigation is this line. The ordnance maps that you use if you're going hiking in the UK are based upon a meridian that's about 2 or 3 meters to the left or right, depending upon which, to the east, west of this line, someplace right there, which is probably why you get lost walking around in England. Okay, that's a joke, but here we go. And so if you ever, this doesn't say 0, what's going on? Now, some of this goes back to earlier work by Christian Huygens. Again, concerning the use of pendulum watches for determining longitude at sea, along with a method of a journal for such watches. This was a big deal. This was, in fact, I would say, like I said, one of the longest lived scientific research projects, going back even earlier to this. There was a competition, earlier competition, 1500, 1550 or so, by the sort of in the Holy Roman Empire and Dutch companies to make a clock. This was based upon, and eventually Galileo was able to, almost 50 years later, and then Huygens was one of the first patents that at the time in 1650 was the most accurate pendulum clock of all time. Now, if I go backwards a little bit, I can give you guys a shout out for all you NIST people. And I think this was actually and is this device actually here, or is this in Gaithersburg? I'm not sure. But basically, this is the most accurate clock on the planet at the moment. Highly, look at the number of years, 300 years between here and here. And we're still working on metrology and trying to understand how to make very, 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 very precise measurements. This is fundamental physics at its best. So on to quantum spectroscopy. I realize I only have about 20 minutes or so to talk. Okay. Well, we'll make this relatively painful as we can, and as I have a lot more to talk about than time will allow. But anyway, so here's the primary. Like I said, I used to be in a chemistry department, and when you start showing equations in chemistry, forget it. So you got to show cartoons, and so this is our basic quantum equation of motion. This is the density matrix. This is the system Hamiltonian, and you have some sort of a dissipator that does this. So the unitary part, which is this, creates wiggles in your system, okay? The dissipator over here, Mr. Sad Guy, has a mallet and maybe a flashlight, and he shines a light on the system, measures the system, and stamps out those wiggles. So we have a competition in an open quantum system between something that wants to create coherences, wiggles in your system, and something that wants the environment that tries to kill the wiggles. Now, any quantum system can be thought of as a clock. Why would this be something interesting? Well, you can have Rabi oscillations in a system, and if you have this thing coupled to an environment, these Rabi oscillations die out as a function of time. And of course, you get a line shape and everything else that's associated with your clock. But you lose coherence in this system. You lose the ability of your system to maintain and this coherent behavior. Nature actually uses this as a way to enhance how excitons in light harvesting systems are propagated through the system. This was a fairly recent paper, 2025, looking at how vibrational coupling in antenna type complexes enhance and preserve the electronic coherences in a biological system. The resonant modes have predicted nearly 50% reduction in the vibrational amplitude and almost zero amplitude. Insights into mechanisms for protecting coherences against a noisy environment. And this is something that is important to think about. Generally, if you ask anybody, does noise in the system what does it do to your quantum degrees of freedom? It says it kills the quantum coherence. Forget it. This is a dumb idea. Don't think about how noise is going to help your quantum coherence. It's going to kill your quantum coherence. Very easy model. Just imagine that you have your energy gap of your system having some sort of fluctuation associated with it. Well, when I calculate a response function, I exponentiate this guy, integrate over time, and I might get something that looks like this. It's almost like a frequency modulation type thing. If I put a bunch of these guys together, I get a bunch of resolutions of this random frequency pattern. Average all of these, and I get a free induction decay. Linear spectroscopy is basically that. I Fourier transform a free induction decay, and I kill coherence. End of story. Let's all go home. Okay, but you can create analogs of this in a very clever way by saying, well, let's imagine that instead of having all my individual quantum states talking to some uncorrelated environment, and let's imagine there's some sort of degree of correlation, which I'll denote by this correlation matrix between the noise that's affecting oscillator I and the noise that's affecting oscillator J. This is a nice Markovian process. I can define a new Ito process. What does that mean? No, let's not go into that. This is basically what's called the Ito lemma that allows me to take a random differential in dW for a Wiener process and turn it into a time increment. And this simply allows the calculus to be very nice and easy to do. And I can write up a correlated dissipator. Nice little analytical problem. And again, just to sort of cut to the chase of this, because I'm running out of time, we can write out the equations of motion for this local Rabi oscillators, exchange interactions, and correlated noise, and we can write up an analytical theory for this. Not a problem. And if we do that, we can do this for fermions, we can do it for spins, we can do it for bosons, we've done it for anyons, and so on. And what you get is a regime, depending upon the strength of this correlation parameter, where I can be in a fully synchronized regime, depending upon the nature, or the nature of the noise, the nature of the correlation between the noise driving oscillator 1 and the noise driving oscillator 2. I can have either a synchronized state if I have anti-correlated noise. I can have a unsynchronized state if I have uncorrelated noise. In other words, each of the oscillators, even though they're basically talking to uncoupled environments. Or I can have correlated noise. Now, what is correlated versus anti-correlated noise? So a correlated noise source would be something like where oscillator number 1 is being pushed like this, and oscillator 2 is sort of randomly being pushed such that, on average, oscillator number 1 and oscillator number 2 are being pushed in the same direction at the same time. Anti-correlated is just the opposite. So what we wind up seeing in this is that the symmetry of the noise spectrum that's pushing your system determines what kind of final state my system will relax into. Now, these are taken at the maximal values of these, of the maximally allowed values of the correlation parameter in our very simple model. Realistically, and anything less than that number will always lead to some sort of relaxation time, relaxation a long time. So fluctuation dissipation theorem is ultimately wins the game in any sort of physical system. But if I push the mathematics of this to these marginal states, I can always wind up in finding these fully synchronized and fully anti-synchronized states independent of what my initial state happens to be. We can average over initial conditions, sample over all possible initial conditions of the system. This is what's called a phase locking value for a set of model parameters. And once I've pushed this correlation past this critical value, and I don't have the equation for this critical value, I think it's shown on the next slide. But it's something that I can calculate from the strength of the dissipation and the energy gap of the system. So it's something that we can calculate analytically. You always see resolution into either a fully anti-synchronized state or a fully synchronized state, depending upon if I have anti-synchronized or synchronized noise, correlated, anti-correlated or correlated noise. always, this is a symmetry that the system has to go into. This is what is called a PT symmetry breaking process. So time reversal symmetry is already broken because I have dissipation. We break parity, which is really the exchange term in our dynamics, being able to swap oscillator 1 for oscillator 2. It's no longer consistent. So I can work out, and I'll spare you the mathematics of this, how I can analyze this is by looking at the eigenvalues of the dynamical matrix, which is really the equations of motion for the quadrature coefficients, really, of the system here. And again, I simply look at the eigenvalues of that matrix. And what you find are what are called exceptional points. And at these critical values of this parameter, and basically where this guy goes to 0. Okay? And where this thing goes to 0, it goes from being something that gives me normal dissipation to something that where I simply have normal oscillations of the system, and to something where one mode of the system is critically damped and the other mode of the system is completely undamped. So by symmetry, the symmetry of the environment can pre-select which symmetry space, what symmetry species of my system survive unscathed due to interaction with an environment. And again, this is very much an idealized model, but it's very ubiquitous, and it's something we've seen in many types of systems that we've looked at. Let me get almost to the end of this, because I want to have some time for questions. A couple of things that we've calculated, which we've done with this. And I'm going to end very soon here so we can, my voice is going because of all the nice dry air that we have. I'm so used to like 70% humidity. What's the humidity here, like 10 or something? I don't know. Okay, and so my voice is getting out. So I'm going to pretty much stop at this point without going much farther. What we found in this is that, okay, this all looks like nice and classical. Maybe this is just by nature of the construction of this. What I haven't talked about is whether or not oscillator number 1 and oscillator number 2, which might be interacting via some sort of coherent channel, they're definitely interacting via some sort of incoherent channel. How much quantum information is shared between this part of the system and that part of the system? So I can turn the coupling parameter off. Okay, and I don't have the analytical version of this in my talk yet, in my talk today, but I can tell you what it is pictorially. You can calculate something which is called the mutual information, and it's basically a measure of how much information is shared between this part of the system with that part of the system. And you can do this for any sort of statistical ensemble. You break it in half and calculate via probability theory and information theory how much information is shared between the two. Okay, well, there's information shared between these two oscillators because they're oscillating in phase with each other. How much of that information is quantum mechanical and how much of that information is classical? Well, you might think this should all be classical information because there is no, if I turn the coupling, the dipole coupling or the exchange coupling off between oscillator 1 and oscillator number 2, that should all be, the only thing that's left is noise that's coupling these two. So naively, and I'm sort of telling you the end of this by saying naively, I thought, well, all the information shared between oscillator number 1, spin number 1, oscillator number 2, spin number 2, should be purely classical. But I can calculate something that's called the discord. And the discord is a measure of how much quantum information is shared between two different states. And if I calculate discord using this system, there's a procedure for doing this, we find that almost 90%, more than 90%, in some cases all of the information shared, depending upon our choices of parameters, depending upon our choices of the noise, and et cetera, is quantum mechanical in nature, even though these two states are not communicating via a quantum channel. And I don't quite, Maybe this is an obvious thing, and maybe I'm just too simple-minded to think why this isn't an obvious thing. But it seems very striking to me that this is two systems interacting, which I would say are classical channels, emerge quantum mechanically entangled. I don't have an answer for why that's the case. I will sort of leave this to sort of give a fast forward of some things that we've played with. We've looked at fractional statistics, which are a new thing for doing quantum computing, and so on. And we do find that you do get entanglements and enhancement of entanglement of anionic fractional statistical systems. You can tune where the synchronization occurs by playing around with the exchange phase. I'm not going to go through this. I apologize for that. You see bifurcation structures, et cetera. We even calculate with the nonlinear spectroscopy signals that you might have for these things. And then recently, you can't stop there. You got to keep going. And if you're going to talk about thermodynamics, you got to talk about Maxwell's demon. We came up with this idea for like, can you use noise as another kind of resource where you have imposed some sort of coherences within your environment using squeeze states? Can I impose some sort of thermodynamic? Can I use squeezing of the photons or the squeezing of the environment as some sort of thermodynamic resource for doing some measure of work? Okay, and there's like these ideas of quantum heat engines and et cetera that people have played around with. The realization can be done in terms of quantum optical systems, optical mechanical systems where you have a cavity and you sort of make one of the cavities vibrate. You can do this with DBR systems and et cetera. So there are, in fact, experiments that one can go back to and look at how these squeezing effects can be realized in an experimental sense. And I apologize that I'm going through this at lightning speed, but let me just get to some of the interesting results that we have. And that is, can we harness coherence in the following way? So imagine that I have, like my two oscillator system, I have a noise source on one side, a noise source on the other side, but instead of being thermal noise, it's non-thermal noise, it's squeezed. You can work out how this works, and what you wind up with are what are called or anomalous rather correlators, B dagger B being a normal correlator, BB and B dagger being the anomalous terms. There's an uncertainty relationship between all of this, and so on and so forth. But what we looked at was whether or not there's any sort of spectroscopic signature of this that can be manifest. So if you apply squeezed light in the input channel of a state, you can work through the Heisenberg equations of motion. You can calculate a spectral response. It's a pencil and paper type idea. You can look at what is the spectral response in the output field given squeezed input. That's the response. That's the equation that one should have. There's two parts to this. This would be the usual thermal term. No squeezing, you get this guy. N is simply the occupation number, average occupation number of your bath. So temperature would go into here. And so you get a nice typical normal Lorentzian, everybody's happy type line shape. Now you put in squeezing, you get this extra term. And what's interesting about this extra term is this is actually due to the fact that you're building coherences, you're forcing the system to have coherences, and you're getting interference between the normal radiative channel and this channel that is driven by having coherences imposed upon it by the nature of the input field. I can calculate a line shape, not a problem. Normal line shape, this is this phase of how I've decided to squeeze the system. Again, an experimental parameter. And this is just a typical Lorentzian. But you can wind up getting really wild-looking line shapes as I change the phase of the squeezing from 0 to 2 pi, rotating around all the way to very strongly squeezed light, giving rise to this very sort of basically two split line shape. Now, this is very asymmetric. So you break reciprocity. One side of the line shape is not symmetric about this guy, right? Now, this got me thinking about what's called the Fano line shape. Fano line shapes are well known. In autoionization, you get this sort of typical line shape, which almost looks like ours, except it's upside down. And these are due in the physical system due to interferences between two competing decay channels that have some sort of coherent crosstalk in between. So you get this is an internal interference effect driven by the dynamics of the system. Ours is an external interference effect due to the fact that I have a coherent light source or a squeezed light source driving transitions of our system. So let me end with that. That one can use the noise of a quantum system or of a reservoir, a thermal system, as a way to do interesting spectroscopy of a system. I sort of throw this out a little bit of an experimental challenge that one can use different kinds of light sources, different kinds of noise as a way to enhance and preserve and maybe even as a resource for doing quantum dynamics. I want to point out some of my collaborators, Andrei Piratinsky at LANL, a longtime collaborator looking at all sorts of different kind of theory things in terms of like anomalous lasing type behaviors. Carlos Silva, a longtime collaborator going back to probably 1995. Hao Li, my postdoc, who is now working for Carlos. This is me and my graduate student having a little discussion over physics. This is Stanislav Ulam, who my fellowship was named after. This is one of my more recent graduate students. And just to have some other pictures I like to show. This was me at my 60th birthday party. He and I survived a car crash on the way out there. And so I think this is meritorious enough to show. So I want to thank you all for your attention. And I entertain questions and comments and et cetera.
Thank you, Eric. It was very dynamic, interesting. Questions from the audience?
Thanks for the nice talk. I have a kind of two-part question. It's on the statement you made about the oscillators, or the two quantum systems coupled to two valves with either correlated or anti-correlated noise. First one's clarification. Is what you were saying that you can have coherent exchange of information between two oscillators if you cut the coherent channel between them off and only use the environment? Is that the statement?
That's a statement that I really don't want to make, but it sounds like I'm forced to making that. It's like I wind up in an entangled state, even though both states are being driven by incoherent noise. Okay, so it's not that I'm exchanging coherent information via some sort of incoherent channel, because that doesn't make any sense to me. But I'm winding up in an entangled state. Even if I start off in an unentangled state, I wind up in an entangled state due to this interaction with the environment.
Could the assumption of correlation or anti-correlation between the two paths implicitly assume some sort of correlated channel between some subset of the back nodes, or?
Yes, yeah, exactly. So yeah, and I think that's exactly what's going on. Is that so? When I work out all of this, I work this out in terms like Lindblad operators and everything else. But really, what is a Lindblad operator? A Lindblad operator is a representation of how a transition can occur, or an interaction between a system and its environment, integrating out all of the environmental degrees of freedom, and use Markov approximation, and so on and so forth, so on and so forth. But buried within that noise term, the spectral density of that is really what you're talking about are phonons or some sort of normal modes of the system. So, in a sense, you can imagine like a correlated channel or a correlated noise channel being, let's say, for example, two spins. So let's say, imagine that I have two energy gaps of two spins that I'm going to force to be in some sort of framework, maybe synthetically prepared using like metaorganic frameworks or something like that, where I have maybe a vibrational normal mode that does this. okay, that modulates the local environments around one spin relative to the other in some sort of anti-symmetric way, okay? Now, formally, I mean, in a fully quantum mechanical sense, that is a quantum mechanical degree of freedom of my system. Now, right? Or any sort of maybe like a symmetric stretching mode that is non-local between the two quantum states that I'm trying to deal with. Now, formally, if the coupling is strong enough, I really should put that back into my system Hamiltonian, right? Because that's now a coherent channel, right? But if it's a weak coupling, I throw that away. I treat it as a noise source. Now, yeah, so yeah, there is this like idea that I can have some sort of like dynamical process within the system. I can even make that a classical noise term, right? I can just have a classical oscillator doing this. There's no quantum mechanical phase e to the IHT type term.